Okay, so what is light? Light is a fascinating topic in physics, and here we go, week 26. So what is light? We draw a light wave kind of like this, and it turns out that there's an electric field and there's a magnetic field. And the electric field, so I'll write this, the electric field, a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. So we have the electric field, and we will get to talk about electricity and magnetism a lot. Magnetic field. So it turns out that the electric field creates a changing magnetic field creates the changing electric field. So it propagates through empty space. So it does not need a medium to pass through, unlike sound waves that need air molecules to vibrate back and forth. And that's that's the basics. There's, of course, a lot more to it. So the electromagnetic spectrum, you probably remember some of this from chemistry. Looks like this. So it turns out all of these are electromagnetic waves. So these are all light. It just turns out that our eyes are perceptive to these certain frequencies or wavelengths. So infrared, that's like heat, and then these are signals that we use to transmit information. All right, X-rays these are higher energy, and so they don't pass through the bone, but they do pass through the skin. So we basically take a photograph using higher energy or higher frequency electromagnetic waves with these, and then these would be really toxic to you. So know that that's about 400 nanometers. We talk about nanometers when we're talking about the wavelength of light, and that would be for the purple end of the spectrum. And then over here, we have about 700 nanometers, and this would be the wavelength for the red end of the visible spectrum, and we can see stuff in between. Remember that Roy G, and then indigo is kind of weird. Is that purple or what? So yeah, Roy G. Biv, okay, for the colors. So it turns out that different frequencies correspond to different colors. That's a key concept in this unit. Different frequencies, different colors. Okay, electromagnetic spectrum. So you drew that somehow in there, maybe got some colors. So light is fast, and it was Einstein who proposed that the speed of light is the same to all observers, which ended up sort of changing our perception of reality. But it turns out that 3 times 10 to the 8th meters per second is the speed of light. That's 300 million. So it's almost a million times as fast as sound. And so the first person was this scientist Michelson, who did an experiment in Southern California, I think, between two mountaintops. And you can imagine a crude example of this experiment. It's these two people, and they're like, hey, how fast does light go? I don't know. I have a flashlight. They'd have to do this in the middle of the night. And I have a flashlight. And this person says, and this person has a stopwatch. So there's a stopwatch. Okay. And this person says, all right, I'm going to start my stopwatch and turn on my flashlight. And you, as soon as you see the light, you turn on your flashlight. And then, so the light goes like this. So the light goes like this. This person sees it, turns on their flashlight, and this person thinks, as soon as I see your flashlight, I'm going to stop the stopwatch. And so, this would be the human error of the person, seeing and starting the flashlight that's what they would be measuring. They wouldn't actually be measuring the speed of light. But Michelson did this, and it was with some sort of a rotating mirror. So there's some laser and some apparatus with maybe a bunch of different mirrors like this. So this would be a top view, and there's a laser, and so the laser does this and goes out here. And if this thing's rotating, 1,000 times a second or something, then the light beam is broken up into these pulses, and so it's something like that, from which he was able to determine the speed of light. For a long time, people thought it was infinite or instantaneous, and so he was the first American to win the Nobel Prize in science. Good for him. Okay, so anyway, light is very fast. It takes about 8 minutes for light to get from the sun to us. And I love thinking about this stuff. There's a question that I pose to students, and so I will pose to you, and that is, do the stars exist? Question. We can talk about that later. So, wave versus particle. So the whole field of quantum mechanics came about in large part due to experiments with light. And we say that that light behaves like a wave, but we say it also behaves like a particle. So we're going to look at diffraction. We're going to see diffraction. And what we can picture is, so here's a light source over here, and these are light waves coming in, and there's some grating, there's some wall with little openings. And so the light waves pass through, and they do this, and we've seen this with speakers and sound waves, where there was constructive and destructive interference. And so it turns out that on the screen, so this is a screen over here, and we're looking at what happens with the light that passes through these two openings and then interferes either constructively or destructively. And it turns out it's very bright and then dim and then bright and then dim and then bright. So bright and then dim and then bright. And if you looked at intensity as a function of distance, it would be something like this. Okay, so very bright, medium bright, little bright, medium bright, little bright, and then dim and dim and dim. So we get constructive interference here and destructive interference there. That would be a good thing to write here. So this is diffraction. We'll look through diffraction gratings and we'll see how it separates different frequencies. So the different frequencies will interfere in different locations. So anyway, that's our brief introduction to quantum mechanics. We do get to talk about this more later, and it's pretty interesting. All right, so it's light, and yes, so color. When you see an orange, it looks orange because that's the light that bounced back towards your eyes. So in school, you learn. So kindergarten, right, we're finger painting. And the primary colors we learned are red and blue and, you guessed it, yellow. So when we mix red and yellow, we know that we get orange. And when we mix red and blue, we know we get purple. And when we mix yellow and blue, we know we get green. And then if we mixed all of them, in reality it ends up being kind of brown, but theoretically, if we had sort of perfect paint, it would end up being black and no light would be reflected. So this is called subtractive mixing, and this happens with paint. The cool thing that is counterintuitive and is new is that when we're mixing colors of light, this is called additive mixing. So this is when we're mixing colors of light, and here's what we're going to see. We'll get to do this in class. We have red and blue, but our third primary color is actually green. What? And when we mix green and red light, what we're going to see is yellow. And I know you don't believe me, and that's cool. I understand. And when we mix red and blue, we get what's called cyan, but it's more of a turquoise. How do I spell turquoise? No idea. Something like that. And when we mix green and blue, we get magenta, which is basically purple. It's kind of a pinkish purple. Pinkish purple. So this is interesting. And then when we mix all three of them, we actually get white light. So we say that white light is made up of all these component colors. And you've seen, where's my Pink Floyd album cover? Oh my gosh. Okay, that'll get put into another video. Sorry. If you know what I'm talking about, the prism. Yeah, anyway. Okay, so different colors of light, and we will get to see more about that. So polarization happens when we have these electric and magnetic fields, and it turns out that, so here's a light wave moving in that direction very quickly, And the electric field is oriented. There's a bunch of them. There's one that's like this, and there's one that's to the side, and there's one that's at some angle. And what a polarizer do, you can polarize light by a filter. So that's essentially what I'm drawing here. So it's basically just one slit that's oriented in a certain direction. So all of the light waves that have their electric field to the side get blocked, and only the one that has the electric field up and down passes through. So we say this is transmitted, and the other that was transmitted, and the others are blocked. So the light is oriented in a certain direction. This is not my normal stylus. That says oriented in, oh my gosh, a certain direction. This is awful. Oh my gosh. Okay, well you're listening to me, right? Thanks. Certain direction. All right, and then stuff can also be polarized by reflection. So I have two things to show you. First, this. So take a look. This is the same situation, but basically, so here we're just looking at this dude posing in the car. Here we're looking at the dude posing in the car, but we're wearing polarized sunglasses. And it turns out that the sunlight that bounces off the window ends up being polarized, so it's oriented in a certain direction, so we can wear polarized sunglasses, and that blocks that light out. So it basically blocks the glare, and what we see is stuff from actually inside the car. Uh-oh, here we go. All right, and this is also kind of interesting. So it's a photograph, and what do you see? Well, you see inside the store, it looks like ice cream and, I don't know, a Christmas tree or whatever, but you're also seeing the opposite side of the street. Behind you, there's some building. So we're seeing a reflection, and we're also seeing light being transmitted in this one image. And the light that is reflected, so the image of the building in the background, would be polarized. So if you were to put polarized sunglasses on, all you'd see is the ice cream store. Okay, so what can we say about reflection? We can say that, if I can write, reflected light gets polarized. So I ask a question: why are some sunglasses polarized, and in what situations might this be helpful? If you look at the video below, there's something about polarized sunglasses and fishing. It's just about a minute. You should watch it. It's pretty cool. And we also use them for driving, or people that are out on the water skiing, or something like that. Okay, thanks.